Hello, class. We're about to start lesson 4-7, just a normal day. Our objectives is to recognize characteristics of data that are normally distributed, to understand the connection between area under a normal curve, percentage, and probability, make an educated guess about the empirical rule, then, then use the rule to calculate percentages and probabilities, and also to compare data values from different sets using z-scores. To study the abnormal is the best way of understanding the normal. William James. If you grew up anywhere near maple trees, you're probably familiar with the seed pods that drop by the thousands in the spring. Like almost all living things, the individual pods vary in size on any given tree. There's a typical size with some pods bigger and some smaller. On a beautiful spring day, I gathered 100 pods from the maple in my backyard, measured each, then grouped them according to their length. The smallest was 42 millimeters, the largest was 59 millimeters. And in the photo, they're grouped in classes 42 to 43, 44 to 45, 46 to 47, etc. An interesting thing happened. We see that the largest number of pods have length somewhere in the middle of the range, and the classes further away from the center have fewer pods. A wide variety of quantities in our world tend to exhibit the same phenomenon. In fact, it's so common that frequency distributions of this type came to be known as normal distributions. That means that if we get really good at studying normal distributions, we'll be able to analyze tons of interesting things in our world. Okay, now we come here at the bottom. It says number one, list some things that you think might be normally distributed. Try not to focus strictly on physical sizes. So we could look at IQ scores, finish times at a race, and scores on an exam. And you can also do SAT scores and also ACT scores. Okay, now we move on to our next page. It says here, suppose a researcher selects a random sample of 100 adult women and measures their heights and constructs a histogram. The researcher will probably get a graph similar to the one shown below. Okay, notice that we omitted a scale on the horizontal axis. Put in a scale that you think seems reasonable based on the description of this histogram. What do you think the value right in the middle of the horizontal axis represents? Okay, so first thing, the value in the middle of the horizontal axis, we would think that the middle value is the mean, because the mean is typically the average, so we would think that the middle value would be the average of these, in this case, the women height. Now, what we could do is this here. Let's assume, for argument's sake, that we start with the lowest height of being 4 feet 7 inches. And then we do 4 feet 10 inches. And then 5 feet 1 inch. 5 feet 4 inches. And then we would have 5 feet 7 inches. And then 5 feet 10 inches. And then finally 6 feet 1 inch. Okay, now it says next, the researcher decides to go big or go home, and she chooses big. She dramatically increases the number of women in the sample, and since she has more data to go on, makes the classes narrower as well. Happy with the result, she adds even more women to her sample and makes the class even narrower. The results will most likely look like the next two graphs. Now it says, now let's use some imagination. Suppose that our researcher has magical powers and continue adding data and improving her histogram until there are infinitely many data points. Wow, that's a lot. Instead of drawing boxes, draw a smooth curve that you think the histogram would become in the long run. So let's try and do a smooth curve here. Okay, that's what the histogram would somewhat look like. And if you look here, it looks similar to this here, similar to this here, and so on. All right, now we're going to move on to problem number 4. Okay, it says if all went well, you've just drawn your first normal probability distribution. We'll see plenty of examples in the remainder of the lesson if you're unsure how well you did. How does the drawing relate to the maple seed pod example from the opening paragraph of this lesson? It's very similar. And just to show you that it's very similar, if you look here, it'll be similar to what I just drew. It's very, very similar. So it's very similar. The largest number of women are close to the mean height with less women as you move toward larger and smaller heights. To show that normal distributions are not even close to a purely mathematical topic, we're going to borrow our definition of normal distribution from an investment site called Investopedia. So we have a probability distribution that plots all of its values in a uh, symmetrical fashion, and most of the results are situated around the probability's mean. It's called a normal distribution. Values are equally likely to plot either above or below the mean. Grouping takes place at values that are close to the mean and then tails off symmetrically away from the mean. Okay, now it says, next we'll highlight some of the important features of a normal distribution, which in turn give us the key features of a data set that is normally distributed. The value in the middle of the distribution, which appears most often in a sample, is the mean. The distribution is symmetric about the mean. This means that the graph has two halves that are mirror images on either side of the mean value. This is the key fact. The area under any portion of the curve is a percentage in decimal form of data values that fall between the values that begin and end that region. Let's explore that last key point because it's what makes normal distribution so useful in analyzing data. The graph below shows a normal distribution for heights of women in the United States. The number on the horizontal axis are heights in inches, and some areas are labeled for reference. What is the mean height for American women? Okay, so basically, if you look here, the mean is basically right in the center, so it'll be 63.7 inches. Now we move on to the next page. It says, what percentage of American women are between 57.4 inches and 59.1 inches tall? You go to 57.4 to 59.1, you see it's 0.034. Change that to a percent. You'll move the decimal 2 places to the right. So it'll be 3.4%. Now, it says if there are 31,806 women in the stands for a college football game, how many of them would you expect to be between 63.7 and 66 inches tall? So first, let's find that percentage. 63.7 to 66 inches, and the area is 0.303. So it'd be 0.303, and that is the area. Okay, so now we have the amount from 63.7 and 66. So we would take that 31,806 women and multiply it by this decimal here. And when we multiply that, it'll give us 9,637 women. And of course, we could put that in decimals just to check that. So we have 31,806 times 0.303. And actually, that should be approximate. And we round it to the nearest whole number. Okay, so now it says here, so now we know that if we have data values that are normally distributed, and if we can find the area under portions of the graph, we can find the percentage of data values that fall in a certain range. That leads to the big question. How in the world do you find areas under the graph? In this lesson, we'll rely on a known rule that allows us to quickly find a range in which most of the data values fall. It's known as the empirical rule. Before seeing the rule, let's make some educated guesses. According to recent research, the mean height for women in the United States is 63.7 inches, which you already knew, right? And the standard deviation is 2.7 inches. The normal graph below is marked with the mean and heights that are 1 and 2 standard deviations above and below the mean. Okay, so now we have this graph here, and we're going to take this information and apply it when we go here to the next page. Okay, problem number 8. It says the total shaded area on the entire graph is 1, and this is true for any normal distributions. Explain why. Think carefully about what we know regarding area under a normal curve. The area represents the percentage of values in that range. All possible values are under the curve, so it is 100% or 1. So if all values are there, we know all means 100%, and 100% written as a decimal is just 1. So that's how we know it's 1 under that value. Okay, number 9. It says make an educated guess as to what percentage of the total shaded area is between 61.0 and 66.4. What does this tell us about women height? Okay, if you look here, 61.0 to 66.4, you look at this, this almost looks like it's taking about close to a third of the graph. So I would say this would be, well, actually it looks, not a third of the graph. It looks more like a little bit more than half because of how high this is. So this has the majority of values. So I would say maybe around 60%. And this is the percentage of women in the population between 61.0 and 66.4 inches tall. Now it says, based on your answer to question 9, estimate the percentage of area between 63.7 and 66.4. So that's like a halfway between these. This is the whole, and then it looks as though 63.7 to 66.4 is half of that. So if we think it's about 60, then I would assume that that's about 30%. I'll put about 30%. Now make an educated guess on the percentage of total shaded area between 58.3 to 69.1. 58.3 to 69.1. If you look at this, 63, let me see, from here to here, we say this is about 60. So if we looking from these two, from here to here, we would think that's about 90%. So I would say about 90%. Okay, now it says, now it's time to see how you did. Okay, we go here to the back. It says the graph to the right shows an illustration of the empirical rule. Recall that X bar is the mean and S is the standard deviation. All right. So it says here, man, I love M&Ms. Can't get enough of them. An absolute true fact. I just finished eating a handful of peanut butter M&Ms, my new favorite. When I buy a bag, the last thing I want is to get shorted. So how many M&Ms is enough? According to a fascinating post on joshmadison.com, the mean number of plain M&Ms in a standard vending machine bag is 54.6 with a standard deviation of 1.3. Let's see how we can use the empirical rule to study what's likely to happen when you buy a random bag from a vending machine. But before we do that, if we look here, when we said that, I forgot what the numbers were. Oh, the 61 to 66.4, we said that was about 60%. It's about 68% according to this graph. And then when we did the 63.7 to 66.4, we said it was about 30, but it's about 34. And then here, from this value to this value that we said was 90%, it was 58.3 to 69.1. We said it was about 90%, it's about 95%, just to give you a basis on this. Now, it says here, if with the solved example 1, using the empirical rule, assuming that the number of M&Ms in a package is normally distributed, which by the way is more than likely, draw an empirical rule diagram using the given mean and standard deviation. Then use your diagram to answer these questions. Okay, now it says here with A, if you buy 200 1-pound bags of M&Ms, a number I guarantee I've surpassed in my lifetime, how many would you expect to contain between 505 and 529 M&Ms? Fill in the blanks. It's likely that 99% of bags contain between blank and blank M&Ms. What percentage of bags would you expect to have more than 529 M&Ms in them? Okay, now it says here, the most important part of this example is the first part. In order to use the empirical rule, it's always a good idea to draw and label a normal distribution with the values corresponding to the key values from the empirical rule label. That means we'll want to start with the mean in the middle, then keep adding and subtracting the standard deviation. Since the key values are 1, 2, 3 standard deviations above and below the mean. The mean in this case is 517, which is listed here, and the standard deviation is 12. So when we go above, we keep adding 12. When we go below, we keep subtracting 12. So We want to label 517 in the middle, then 505, 493, 481. That's what you keep subtracting 12. Working left from the mean in 529, 541, and 553, working to the right. That means you add the 12. And the 12 that you're adding and subtracting is the standard deviation. Okay, now this is continued. It says here, the thing that makes this an empirical rule problem is that the boundaries were asked about 505 and 529 are both labeled on our graph. The first is one standard deviation below the mean, and the second is one standard deviation above the mean. The diagram shows that this corresponds to 68% of the 200 bags. So we'd expect that 0.68 times 200 is 136 bags will contain between 505 and 529 M&Ms. Now, if you look here, the 505, the 529, 34% and 34% add them together gives you 68%. So that's where they got the 68% from. Now it says, according to the empirical rule, over 99% of all data values will fall between the mean minus 3 standard deviations and the mean plus 3 standard deviations. In this case, that's between 481 and 553. So 99% of 1 pound bags will likely contain somewhere between 481 and 553 M&Ms. Now it says here, bags with more than 529 M&Ms correspond to the portion of the graph above 529 on a horizontal axis. Adding up to the areas to the right of 529, we get 13.5% plus 2.35% plus 0.15%, which equals to 16%. So we'd expect that about 16% of bags will have more than 529 M&Ms. So let's go here, back here. We have 529. When you look here, we get the 13.5% from here, the 2.35% from here, and then finally the 0.15% from here. And that's how we got our 16%. Now it says here, now let's see if you can use what you learned and solve example 1 to answer some similar questions. Okay, number 1, what percentage of bags have less than 493 M&Ms? Okay, so let's look here. So we'll go to 493, and we look at the percentage of bags with less than 493. So it'd be 2.35% plus 0.15%, which is 2.5%. Okay, next. It says, how unusual would it be to get a bag with more than 553 M&Ms or less than 481? Okay, so if you look at it, they said, how unusual would it be? So we need to add those percentages up. So we have more than 553, that'll be 0.15%, or less than 481, and that'll be another 0.15%. So that'll be 0.30%. So it'll be 0.30%. That's how likely it would be for you to get these two, 553 or less than 550, higher than 553 or less than 481. Okay, now we move on. It says a quantity that can vary randomly from one individual trial to another, like the number of M&Ms in a randomly selected bag, is called a random variable. Why? Because it's random and it can vary. See, math does make sense. If you're really sharp, you may have thought about the connection between the percentages we've been calculating in this lesson and probability. If you haven't, we're going to ask you to do so now. Okay, using what we know about area under a normal curve and percentage of data values, what does the area under the curve between two data values tell us about probability for a random variable? So we could say that the area is the decimal form of the percentage. The decimal form is the probability. So number 2, it says based on the work you did earlier, what's the probability that the next 1 pound bag of M&Ms you buy will have between 529 and 544 M&Ms in it? Briefly describe how you got your answer. So we have 529 to 541, which will give us the 13.5%. So we would do 0.135. Okay, so basically we will find the percentage in that range and change it to a decimal. So just as indicated, we had the 0.135, but on the table we had 13.5%, which we would change to 0.135. So that's basically it. Okay, now we come down to here with what is called z-scores. It says, as you probably know, there are two main standardized college entrance exams, the ACT and SAT. Since each has a completely different scoring scale, it's really difficult to compare the scores of students who took different exams. Do you think that scores for these exams are normally distributed? And I would have to say yes. Most people score close to the mean, with less scoring more or less than the mean. Say one way to compare statistics drawn from different populations is to compare how far above or below the mean they are. The z-score is a statistical measure that was designed to do exactly that. So we have the mean, and then we have the S, or the lowercase sigma. So this is the data point is 1 standard deviation above the mean. All right. So now we go here. It says a z-score tells you how many standard deviations the data value is from the mean. The data value on the line above would have a z-score of 1 because it is 1 standard deviation above the mean. Data values that are below the mean would have negative z-scores. Fill in the blanks in the diagram with z-scores using the description at the bottom of the previous page. So basically here, right here in the middle is the mean. So your z-score would be 0. Because remember, your z-score tells how many standard deviations it is from the mean. And the mean would be 0 because there's no standard deviations away from itself. So here, this would be 1, 2, and 3. This would be -1, -2, and -3. So that's how far standard deviations they are from the mean. Okay, now it says using z-scores, this is solve example 2. A standardized test of intelligence is scaled so that the mean IQ is 100 and the standard deviation is 15. Find the z-scores for a person with an IQ of 85 and one with the IQ of 115. What's the probability that a randomly chosen person has an IQ between 85 and 115? Okay, now A, it says this is the answer to A. It says this is all about understanding what z-scores actually mean. Notice that the mean is given as 100 and the standard deviation is 15. That means that 85 is exactly one standard deviation below the mean, and 115 is exactly one standard deviation above the mean. The z-score for a data value is the number of standard deviation it is above positive z-score or below negative z-score, the mean. So 85, one standard deviation below the mean, corresponds to z-score of -1. And 115, one standard deviation above the mean, corresponds to a z-score of 1. And we look here at B. Now we're back to interpreting the empirical rule diagram. We can see that 68% of the area lives between z is equal to -1 and z equals 1. The total area under the normal curve is 1. So 68% of the area is 0.68, and that's the probability that our chosen individual has an IQ between 85 and 115. So if we look here at number 5, it says if a data value has a z-score of blank, then half of the data are below the value and half are above. That describes the mean, which has a z-score of 0. We know that the center of the normal distribution is the mean for a random variable. What does question 5 tell you is also true about the center of the distribution? It is also the median. Because remember, the median is right in the center, has just as many values above as it has below the value. So it's also the median. Now we go here to the back. It says here, a job applicant is told that their IQ score measured in the screening process is higher than 84% of the general population. What was their z-score and their IQ? Okay, so if we go back here, we want to know what their IQ is and also their z-score. So we need to add up these percentages. Now they said it's higher than 84%. So what we would do, we would start here and go until we hit about 84%. So if you look here, this is 0. Let me put this in decimals. So we had 0.15. Now I'm not going to put the percent. I'm just going to put them as their decimal form without the percent sign. 2.35 plus 13.5 plus 34 plus 34. So if you notice here, this is 84, and we know that's 84%. So it ends at this last 34, which is a z-score of 1. So we will put z equals 1, and then our IQ at 1 z-score, we know the mean is 100, standard deviation is 15, so the IQ is 115. Now, it says computing z-scores. Now it says for a data value from a sample with mean x bar and standard deviation s, or from a population with mean mu and standard deviation is supposed to be lowercase sigma, the z-score is, and then they give us the formula here. All right, now it says here, a data point is greater than the mean if z is greater than 0 and less than the mean if z is less than 0. Z-scores have no units. Z-scores are typically rounded to 2 decimal places. So now it says 1 year the ACT had a mean score of 21.2 and a standard deviation of 5.1. That same year, the SAT had a mean score of 1,060 and a standard deviation of 195. Suppose that a scholarship committee is considering two students, one who scored 26 on the ACT and another who scored 1,230 on the SAT. Both are pretty good scores, but which one is better? That's not so easy to decide because the scales are totally different. Now it says first instinct, which score sounds better to you? The SAT, because it sounds much higher. Now it says find the Z-score for each test score. So we had an ACT, and we're told with the ACT, the mean score is 21.2, and this person scored a 26. So we'd take 26 minus the 21.2, and it'd be 4.8 points above the mean. So now we would do the formula, the Z formula. So we have 4.8 divided by the 5.1 because it says a standard deviation of 5.1. Now when we divide that, that would give us 0.94. Now we would do the SAT. The SAT, we're told here that this person scored a 1230 and that the mean score is 1,060. So we do 1230 minus 1,060, which would be, what's that, 170. All right. So then we would take this Z and we would have 170 over, we're told that the standard deviation is 195. So we divide that by 195. So 170 divided by 195 would give us, if we round this to two decimal places, it'll give us 0.87. So basically, we notice here that the ACT has a higher Z-score, so it's the better score. So now we come here to number 10. It says describe exactly what each Z-score tells us. So the ACT, the Z-score is 0.94. So a 26 on the ACT was 0.94 standard deviations above the mean. The SAT, his Z-score was 0.87. So a 1200, what was it, 1230 on the SAT was 0.87 standard deviations above the mean. Now it says number 14, based on the Z-scores, which would you say was a better score and why? The ACT, because it was more standard deviations above the mean. Now, It says big sports fans tend to love arguing, and one of their favorite types of argument is who was better, Michael or LeBron, Montana or Manning, Kershaw or Koufax. Blogs and airwaves are filled with arguments of this type. And what makes it so difficult to decide is that players and teams from different eras are hard to compare statistically because sports evolve. And what might have been an amazing statistic 50 years ago could be completely pedestrian today. Fortunately, this is exactly the kind of thing that studying statistics analytically is good for. Says the 1942 St. Louis Cardinals were one of the all-time great baseball teams. They won 106 games in an era when teams played only 154 games in a regular season. During the 1942 season, the mean number of games won by a National League team was 75.8 with a standard deviation of 20.5. So mean standard deviation. Another great Cardinals team was the 2004 squad, which won 105 out of 162 games. In 2004, the mean number of games won by a National League team was 80.9 with a standard deviation of 13.6. Based strictly on winning percentages, the percent of games won, that is, which was the better team. So we had 1942, they won 106 games. No, wait a minute. Okay. I was supposed to underline this 106 games out of 154 games. So that'll be approximately 68.8% won. Now you put that in your calculator to give you the decimal 0.688 and you round. So 2004, it was 105 over 162. And that would give you about 64.8% that was won. So based on percentage, the 1942 team won. So basically, when I said won, they were better, I should say, based upon those percentages. Now we come to the back here. It says use information besides the winning percentages in the preceding paragraph to make a good statistical argument about which team was better. Obviously, showing your work is a must. Write your final answer in the form of a few sentences showing you know what you are talking about. So we would be basically looking at using z-scores for both of these years. So let's go through the z-score formula. Okay, so now we do these z-scores. So we have 1942. We have our z is equal to 106 minus 75.8 divided by 20.5. Now we got all this information from the previous problem. Now if we look back here, we have our 106 games. We have our mean average, which was 75.8. And then we have our standard deviation, which was 20.5. Now, after we solve this, we had 30.2 divided by 20.5, which gives us 1.47 for our z-score. Now, in 2004, our z-score would be 105 minus 80.9 divided by 13.6, which is equal to 24.1 divided by 13.6, which is 1.77. So the 2014 is better in terms of being more standard deviations, above the mean, compared to the other teams. That year. Now we come down here to the last problem. It says, look back at your answer to question 1 on the first page of this lesson. How did you do? Would you be able to come up with more examples now? Say I did pretty well. We can now add heights, which is basically from the problem with the women and their heights, weights, and candy in a package. So that is basically it from section 4 of 7. If you have any questions, please contact me.